So talking about different ways of presenting and communicating with numerical figures and data then, so one option is frequency tables. So again, the main point here is communication and presentation of information, and frequency tables are used in order to organize data in a systematic way as possible, and this is important especially for larger data sets. And it might sound a bit lame to talk about this now, but this will be really important, this being systematic bit when it comes to real projects and real data sets. This may also be used to create further graphs and tables, for example frequency polygons and histograms, and I can't deny that this isn't amazingly exciting, but it does touch on important wider themes here. So certainly as far as accounting and finance are concerned, general numeracy and this sort of attention to detail. Also, what I would emphasize here when you've got a real data set is this sort of being systematic. So in my experience, if you've got a large data set, okay, it's not necessarily obvious what to do, and it's possible to make all sorts of mistakes if you're not sufficiently systematic. Alternatively, if you are systematic, you'll be amazed at the mistakes and everything else that you can sort of suddenly spot, precisely because you've got all the fundamentals right in the analysis. Tables then, so we've got this sort of small data set here on mortgage interest rates, and then you can rearrange this into a frequency table as follows. So the first column is an interval. So what you've done here is you're just sort of grouping the data set into nice and even and sensibly constructed intervals. The frequency is just a count of the number of times you have an observation within the lower and the upper boundary of the interval. And again, used to sort of just make sure that you're constructing these intervals in a logical and clear way. So usually you would expect these intervals and passing points to be nice round numbers. Relative frequency is just the probability of being in a certain category. So if you add up all the relative frequencies, these should add up to 1, and the cumulative frequency is just the running total. So for instance, what you're doing here is you've got one observation in the first category, observations are the first category or the second category, either the first, the second, or the third categories, etc. So the components of the frequency table then, so the first thing is an interval. This is a convenient grouping of the observations. Again, the name of the game is just to be as clear as possible in your communication. These numbers are usually round numbers ending in either 5 or 10. The frequency just gives observations in each category. So for instance, you 7 observations that fall into this category here is 6.79. The frequency is 7. And it isn't terribly exciting, I'm afraid, but it's easy to make a mistake here if you don't pay close enough attention to detail. And this attention to detail thing would be essential for accounting and finance and for mathematics and statistics. Now, the midpoint is just the average of the upper boundary and the lower boundary. It's often needed for subsequent additional computations, like the frequency polygon I'll talk about in a moment. So this sometimes give a useful way of visualizing the data in its own right. And what I suggest here is you'd expect the upper boundary and the lower boundary to be nice regular numbers if you've done this correctly, because the name of the game here is just to do something that is as easy as possible to communicate. The relative frequency is just a probability of being in the, so it's just the in that category over the total number of the sample. Equivalently, the relative frequency is just the class frequency number. It's not necessarily explained as well as it might have been in the notes, but the relative frequency is just the probability of being in a certain category. in the previous slide, you've got 7 observations in this category, 6.7, 6.9 sample, so the relative frequency is just 7 by 40. The probability of being in this category is 7 observations over 40 in a sample, gives you the number there. Similarly, if you've got 13 observations in this category here, the relative frequency is number 13 observations over the 40 observations in the sample. So it says there that relative frequency is a proportion between 0 and 1, measuring how common each category is. It is just a probability. That's possibly a better way of expressing it. You should have that the sum of all the relative frequencies should equal to 1. So I always vividly remember my high school maths teacher explaining it like this. To accumulate means to gather, so the cumulative frequency is just the frequency of all the observations that you sort of gather as you go down the table and collect all the different that make up the entire sample. So to think of this as the running total of all the previous observations, and then just as recap the frequency table of a couple of slides ago. So there's one observation in the first category, so the cumulative frequency that goes with that is 1. There's 2 observations in the second category, so in the first 2 categories you've accumulated 1 plus 2 equals 3 observations, so the cumulative frequency for the second category is 3. And again, cumulative refers to the word accumulate to gather, so you just come before and the also, for instance, now if you look at the category, you've got 7 observations in here plus the cumulative frequency of 3 from the previous 2 categories. So this 7 in this category, it gives you a value of 10 for the cumulative frequency of this third category. And then one of the things you might do here is to construct a frequency polygon. So a frequency polygon is just a plot of the class midpoint against cumulative frequency, and I will give some Excel examples on the module canvas page of these frequency polygons. It's not for me to do these Excel examples in these lecture recordings. Now, the point of this sort of frequency polygon is it just gives you a flavour of the shape, the to plot these cumulative frequencies, and really what should happen in here, this frequency polygon is not a straight line, then there is some interesting facet in the data. Okay, so here, if we look at our frequency polygon here, the frequency polygon isn't just one straight line. A question of so the fact that it's not just one straight line does indicate there's some pattern of interest here in this data that might be worth further investigation. A lot of the cumulative frequency. So in order to construct frequency polygons in Excel, what you need is a column of midpoint values and a column of cumulative frequencies, I should say, side by side. Now the column of class midpoint values needs to be left. Not as easy as you might first imagine here. If you haven't got these columns the right way around, it's possible to make a bit of a horlicks of it. But what you need, should say there, on the left of a column of cumulative frequency values, and then you would highlight them, and what you need is insert, scatter with straight lines. I will make sure that there's some Excel examples of this on the Canvas module page. Okay, data does have to be organised like this in order to sense, and I will say here as well that it's sometimes a useful trick just to sort of check that any graphs that you produce actually do make sense. So if you try and do this frequency polygon and you make a mistake of it, like you might not have the data organised the correct way around, a column of midpoint values, and on the right hand side, a column of cumulative frequencies. So histograms are another thing that's hopefully vaguely familiar from high school maths. They're actually used quite often in reports and papers to support other analyses that are performed. So they are essentially a bar chart of the group. It's kind of obvious that a histogram is a sort of bar chart or a cousin of a bar chart. It's maybe not so obvious that when you're looking at histograms, the data itself has to be grouped. So in order to do this in Excel, you need a column of category names to the left of a column is. So again, you need the data to be organised in the right format, otherwise you can make it up. Looks of it, Excel can be a little bit unforgiving like this. Highlight the two columns, insert bar, 2D bar. And as I said before, it's worth just checking that the graphs actually do what you think they're doing, and if there is a mistake here, the obvious thing that you might not have done is to have the right way around. You need the column of category names to the left of a column of observed frequencies. So far, nice and easy then, but what happens if you've got classes that are not all of equal size? Instead is something called frequency density. So essentially what happens is that if you've got classes that are all of equal size, then frequency is obviously the thing to look at. If the classes are not all of equal size, then you need to make an adjustment for that using this thing here called frequency density. And the frequency density is just the frequency, the class width. And then you can express this bound. It is intended to be logically constructed, and again, the name of the game is communication. The frequency density just measures how likely a class is to occur once the different class widths have been taken into account. So by adding width on the bottom, necessarily make this adjustment between unequal class sizes. Okay, so if you've got classes that are of different widths, frequency isn't necessarily a natural way to compare them, or the best way to compare them, unless you take into account the different class widths using this notion here of frequency density. That's a bit of a dibbly-dobbly example of frequency density with unequal class sizes. So suppose you've got the following data on people's ages. So you might think there's relatively more people in the sort of fairly extreme of age 60 to 100 years to people aged in years if you just look at the frequency. So you've got 15 people in this sample aged 0 to 15, 20 people are 60 to 100. You scale by the different class widths, the frequency density of this frequency density of this larger 60 to 100 category is 0.5. So you can sort of see here, once you make this correction for the are actually people in 0 to 15 category than in this 60 to 100 category. This makes sense as this is sort of quite an extreme category, age 60 to 100 years. The main point here is just to sort of communicate in a sensible way. Here this is done by calculating the frequency density, which makes this correction for differing class widths.